Swayam Prabha. Digital India. Educated India.
Okay. Now, in continuation of the sum and product, then we have to go to the sum and transformation of random variable. Consider two random variable x and comma y which states x comma y in RD, then expectation of x plus y equal to expectation of x plus expectation of y, expectation of x minus y equal to e of x minus e of y, and variance of x plus y equal to variance of x plus variance of y plus covariance of x comma y plus covariance of y comma x. Expectation of x minus y is variance of x plus variance of y minus covariance of x comma y minus covariance of y comma x. Mean and covariance exhibit some useful properties when it comes to affine transformation. Already we discussed of a random variable. Consider a random variable x with the mu mean and covariance matrix summation. So, affine transformation is y equal to ax plus b, where then y itself is a random variable when mean vector and covariance matrices are given by e of y over y equal to e of ax plus b over x equal to a into e of x over x plus b, which is equal to a into mu plus b. So, variance of y over y equal to variance of ax plus b over x equal to variance of ax space x plus equal to a of variance of x over x into a transpose, which is equal to a into summation a transpose. So, this is respectively we call what? Mean and covariance of a random variable. Now, the covariance of x comma y is expectation of x of ax plus b whole transpose minus expectation of x into expectation of ax plus b. So, expectation of x b transpose into expectation of x x transpose a transpose minus mu into b transpose minus mu transpose a transpose. So, mu b transpose minus mu b transpose plus expectation of x x transpose minus mu transpose a transpose, which is equal to summation a transpose, where summation is equal to expectation of x x transpose minus mu transpose is the covariance of x. Next, statistical independence. So, the definition independent says that two random variable x comma y are statistically independent if and only if probability of x comma y equal to probability of x into probability of y. So, intuitively two random variable x and y are independent. The values of y does not add the additional information about x. If x and y are statistically independent, then probability of y over x equal to probability of y, and probability of x over y equal to probability of x, and variance of x comma y of x plus y equal to variance of x plus variance of y, and covariance of x comma y equal to 0. So, these 4 points are most important, and we have to remember, it will be very useful to use in the machine learning technique. Consider random variable x with 0 mean, expectation of x is equal to 0 and expectation of x cube equal to 0. Let y equal to x square, you take it, and then consider the covariance of equation 3.36 between the x and y. We can write covariance of xy equal to expectation of xy into expectation of x into expectation of y. So, expectation of x cube is 0, therefore, the resultant is expectation of x cube, ultimately the value becomes 0. So, this is one of the example we can calculate. If you know expectation of x 0 and we directly write in terms of the what expectation of x cube, so that the covariance can be easily calculated. In machine learning, we often consider the problem that can be modeled as independent and identical distribution, that is IID, represent identical distributed random variable, n random variable x1, x2 and so on x1. So, for more than 2 random variable, the word independent usually refers to the mutually independent random variable, where all subsets are independent. Therefore, the phrase identically distributed means that all the random variable are from the same distribution. Next, conditional independence. 2 random variable x and y are conditionally independent if probability of x comma y over z equal to probability of x over z into probability of y over z for all z in z, where z is a set of states of random variable z. We write x is conditionally y over z and the bivariate of x comma y over z denoted by x conditionally independent of y given z. So, this is the meaning of conditional independence. So, this definition says that the relation of the equation 55 must hold true for every value of z. So, the interpretation can be understood given the knowledge about the z, and the distribution of x comma y are factorizes, and independence can be cast in the special case of the conditional independence. If x is a conditionally y over mt, therefore, the product of the probability can be left hand side is obtained by probability of x comma y over z is equal to probability of x over y comma z into probability of y over z. By comparing the right hand side, we see that probability of y over z appears in both of them. Therefore, probability of x over y comma z equal to probability of x over z. So, the equation provides an alternative definition of the conditional independence. So, x is conditionally y over z is demonstrated like this. So, the alternative presentation is interpretation of the given that we know z, the knowledge about the y does not change knowledge of x. So, this is the definition you have to remember of x conditionally y over z. Now, we will go to the inner product of random variable. So, already we discussed in the unit 2 inner product, and then we mix together with the random variable. So, we have a 2 uncorrelated random variable x comma y, then v of x plus y equal to v of x plus v of y. Since the variance are measured in the square units and it looks like Pythagorean theorem, hypotenuse square equal to sum of the leg square, and rather we can write the theorem for right triangle c square equal to a square plus b square. So, this is the picture representation of a right angle triangle of the 2 random variable x and y, and this is are uncorrelated, and they are orthogonal vectors in corresponding the vector of a and b, because a and b are perpendicular to one another, and with the help of the right angle triangle using the Pythagorean theorem, hypotenuse square equal to sum of the leg square. Therefore, the root of variance of x, variance of y equal to root of variance of x plus y. So, this way we can bring the result from using the Pythagorean. So, a square plus b square equal to c square. Now, we have a random variable can be considered the vectors in a vector space. We define inner product x comma y corresponding to covariant of x comma y, that is the mixing of inner product and statistics in the random variable. So, the geometric properties of random variable we define inner product x comma y equal to covariance of x comma y for 0 mean random variable x and y. So, we obtain an inner product, we see that the covariance is symmetric and positive definite. So, and linear in the either argument. So, the length of the random variable is norm x equal to root of covariance of x comma x, which is equal to root of variance of x equal to sigma x is the standard deviation. So, it represents standard deviation. So, the longer the random variable and more uncertain. So, the random variable of length is 0 is deterministic. So, if you look to the angle between the two random variable x and y, then cos theta equal to inner product x comma y by norm x into norm y. So, inner product x comma y as per the equation 0.59 represent covariance of xy, therefore, numerator is covariance of xy divided by root of v of x into v of y. So, this is the equation 6 to 1, which is the correlation between the two random variable. This means the correlation as the cosines of the angle between the two random variable. So, we consider them the geometrically. Therefore, if x is perpendicular to y, then the inner product is 0. So, in this case x and y are orthogonal if and only if the covariance of x comma y equal to 0, they are uncorrelated. So, as per the figure, they illustrated the relation in between that the uncorrelated of the two function of the Gaussian distribution of two random variable. So, it is tempting to use the Euclidean distance and to compare the probability distribution. So, unfortunately, it is not the best way to obtain the distance between the distribution. So, this is constructed from the preceding definition of the inner product. So, P of x1 x2 is 2 and P of x1 x2 is a 3-dimensional effect of this curve related to Pythagorean related ideas. So, this is called as Gaussian distribution of two random variable x and y. So, that is the bridge between the inner product and statistics way of expression. Now, recall the probability mass density function is a positive, if this needs add to 1. So, this condition means that the distribution will live on something called a statistical manifold. So, the study of the space of the probability distribution is called as information geometry, and computing the distribution between the distributions are often done using the Gullbach-Leibler divergence, and it is a generalization of the distances that account for the properties of statistical manifold. So, just like the Euclidean distance is a special case of metric. So, Gullbach-Leibler divergence is a special case of two most general cases of the divergence, called it as Bregman divergence and F divergence. So, the study of divergence is beyond the scope of this lecture. So, we refer more details in the recent book Amari. So, one of the founders of the field of the information geometry. Next, we will go to discuss the Gaussian distribution. Gaussian distribution is the most well studied probability distribution for continuous valued random variable. It is also referred to the normal distribution. So, its importance originates from the fact that it has many computational convenient properties, which we will discussing in the following. There are many other areas of machine learning that is also benefit from using the Gaussian distribution. For example, the Gaussian process, variational inference and reinforcement learning. It is also widely used in other application areas such as signal processing. Example, Kalman filter. Another one is a control linear, example linear quadratic regulator, and another one is a statistics. These are all the applications area we can use this Gaussian distribution. So, in statistics we have to use hypothesis testing and a control theory and related to linear quadratic regulator. So, and more example in the Gaussian distribution with 100 samples, right, and it has a univariate. First picture shows that univariate Gaussian, the red cross shows the mean and the red line shows that extents of the variance, and corresponding we have a multivariate. So, a lot of ring will come. So, this is Gaussian viewed from the top. So, the red cross shows the mean and colored lines the contour lines of the density. So, this way we can demonstrate the pictures of the Gaussian distribution and collected 100 samples. Now, the univariate random variable of the Gaussian distribution as a density function is given by x over mu of sigma square equal to 1 by 2 root of 2 pi sigma square of expectation of minus of x minus mu the whole square by 2 sigma square. So, the multivariate Gaussian distribution is fully characterized by mean vector mu, and the covariance summation is defined as p of x by mu comma sigma is 2 pi whole power minus d by 2 of modulus of summation of minus of into expectation of minus of into x minus mu the whole transpose summation inverse of x minus mu. So, where x in RD, we write p of x equal to n of x by mu summation, or x is approximately n of mu comma sigma. So, this figure shows that bivariate Gaussian mesh, and corresponding tour is a contour tour of the plot, and a 6.8 shows a univariate Gaussian of bivariant corresponding samples. So, these are all the special cases of this in terms of bivariate, univariate Gaussian and bivariate Gaussian. So, these are all the special cases of Gaussian with 0 mean and identical covariance, that is mean mu equal to 0 and summation equal to I is referred as a standard normal distribution of this picture. Next, for the marginals and condition of Gaussian or Gaussian. Marginal and conditions of Gaussians or Gaussian. To consider the effect of applying the sum rule of probability and the effect of condition, we explicitly write the Gaussian distribution in terms of concatenated states x transpose y transpose whole transpose, so that probability of x comma y equal to n of mu x mu y of a matrix representation of summation xx, summation xy, summation yx, summation yy. So, this is called as probability of x comma y for the sum rule of the probability, and we have a Gaussian distribution like that. Summation xx stands for covariance of xx, summation yy stands for covariance of yy or the marginal covariance of the matrix x and y respectively. Summation xy equal to covariance of xy is the cross covariance matrix of x and y. So, the conditional distribution P of x comma y is also Gaussian and is given by P of x by y equal to n of mu of x over y into summation x over y, and mu of x over y equal to mu x plus summation xy into summation yy inverse of y minus mu y, and summation x over y equal to summation xx minus summation xy into summation yy inverse of yx. So, note that the computation of the mean in 6.66, the y value is an observation and no longer random. So, note the conditional Gaussian distribution shows how it is more important in the distribution function, and it shows that many places, and we interested to posterior of distribution in Kalman filter, Gaussian process and Gaussian models. In Kalman filter, one of the most central algorithm for state estimation in signal processing and does nothing but computing Gaussian conditions of joint distribution, and one may refer a Dyson-Roth, you can understand. And then Gaussian process is a which or a practical implementation of the distribution over function, refer Rasmussen and Williams. In a Gaussian process, we will make an assumption of joint Gaussianity of random variables. By conditioning on observed data, we can determine the posterior distribution over the function. So, the latent linear Gaussian models, which include the probabilistic principal component analysis and we will look at PPCA in more detail in the section and refer Rovies and Gagramani, Murphy or the 3 others, and based on the principal component analysis by tipping, and these are all the further we have to look into principal component analysis. So, the marginal distribution P of x of the joint Gaussian distribution is itself a Gaussian, and computed by applying this sum rule P of x equal to integral P of x comma y dy is equal to n of x over mu x comma summation xx. So, the corresponding result holds for P of y, which is obtained by marginalizing with respect to x and intuitively looking at the joint distribution of the equation 64, and we ignore everything we are not interested in, therefore, we illustrated in the figure 6.9b. So, this is the bivariate Gaussian of A, and 2 B is a marginal of the joint Gaussian distribution, and C represents the conditional distribution of the Gaussian is also Gaussian. So, this way we can write in terms of the picturization of probability of x1 and mean corresponding to 2 times of the deviation, and then P of x1 by x2 equal to minus 1 and corresponding to mean to 2 sigma, and the further it represents the Gaussian. Now, based on this we have some example. Consider bivariate Gaussian distribution P of x1 x2 equal to n of 0 comma 2, 0.3 minus 1 minus 1 5. So, we can compute the parameters of univariate Gaussian and condition of x2 equal to minus 1. So, we obtain the mean and variance respectively, and numerically mu of x1 over x2 equal to minus 1 equal to 0 plus minus 1 into 0.2 into minus 1 minus 2 equal to 0.6, and standard deviation is equal to 0.3 minus of minus into 0.02 into minus 1 equal to 0.1, applying in the formula of 66 and 67, and using the x2 equal to minus 1 and supply that you can get it. So, x1 equal to 0. So, using 66, so this is 66 and 67 of the formula of a mu of x over y and mu of x over y. So, that we have a mean as well as standard deviation. So, the conditional Gaussian is given by probability of x1 by x2 equal to minus 1 is n of these two combined, you have n of 0.6 and 0.1. So, this way we can calculate conditional Gaussian distribution. So, the marginal distribution P of x1 is in contrast can be obtained by applying the equation 68. So, this is 68. So, that we can write the essential using of the mean and the variance of the random variable x1 is given by P of x1 equal to n of 0 comma 0.3. Next, we are going to discuss the product of Gaussian densities. Now, apply Bayesian theorem to compute the posterior, which result in the multiplication of the likelihood and the prior that multiplication of the two Gaussian densities. The product of two Gaussians n of x over a comma a and n of x over b of b is a Gaussian distribution, the scaled C in R given by C of n of x over C of C with C is equal to A inverse plus B inverse the whole inverse, or C equal to C of A inverse A plus B inverse B, therefore C equal to 2 pi whole power minus d by 2 over A plus B over minus of is the expectation of minus of into A minus B whole transpose into A plus B the whole inverse of A minus B. So, therefore, the scaling constant C itself can be written in the form of the Gaussian density either in A or B with inflated covariance matrix A plus B as what C of n of A over B comma A plus B equal to n of B over A of A plus B. So, we have a note for the notation convenience. We will sometimes use n of x over m comma s to describe the functional form of the Gaussian density, even if x is not a random variable. So, we have just done in the preceding demonstration when we write C equal to n of A over B comma A plus B equal to n of B over A of A plus B. So, hence neither A nor B are random variable. However, writing C in the way of more compact than the equation 7-6. So, the sum related to Gaussian random variable in terms of x and y are independent Gaussian random variable, then the joint distribution of P of xy equal to probability of x into probability of y, where probability of x is n of x comma x over mu x comma summation x, and P of y equal to n over n of y over mu y comma summation y. Then x plus y is also a Gaussian distributed and given by probability of xy equal to n of mu x plus mu y comma summation x plus summation y. Knowing that P of x plus y is a Gaussian, so the mean and covariance be determined immediately using the result from 46 and 49. So, this property will be important when we compare to IID. Therefore, the Gaussian noise acting on the random variable as in the case of the linear regression. Based on the example, since the expectation of linear operation, so we can obtain the weighted sum of independent Gaussian random variable is probability of Ax plus By equal to n of A into mu x plus B into mu y, comma A square into summation x plus B square into summation y. So, note a case that will be useful in chapter 11 in the weighted sum of the Gaussian densities. So, this is different from weighted sum of the Gaussian random variables. Now, we have a theorem. Consider mixture of two univariate Gaussian densities P of x equal to alpha into P1x into 1 minus alpha into P2 of x, where alpha is a scalar lies between 0 to 1 is a mixture weight, and P1 and P2 are a univariate Gaussian density function, and mu of sigma 1 square is not equal to mu 2 of sigma 2 square. So, this means the mixture of the density is a weighted sum, and mean of each random variable E of x equal to alpha into mu 1 plus 1 minus alpha into mu 2. So, the variance of the mixture density P of x is given by V of x equal to alpha into sigma 1 square plus 1 minus alpha into sigma 2 square plus alpha into mu 1 square plus 1 minus alpha into mu 2 square minus of alpha mu 1 plus 1 minus alpha into mu 2 the whole square. So, this is the meaning of variance of the mixture. So, note the preceding derivation holds for any density. So, the Gaussian is fully determined by the mean and variance. So, the mixture is a density can be determined in a closed form. Next, law of total variance. So, in 6.82 we have what is an example of the conditional variance formula is known as law of total variance. So, it generally states that two random variable x and y of variance of x equal to sigma of expectation of p of x plus py. So, the variance of x is expected conditional variance plus the variance of the conditional mean. Consider a Gaussian distributed random variable x over the n of mu comma summation for given matrix A of the appropriate shape. Let y be the random variable such that y equal to Ax is a transformed version of x. Now, we compute the mean of y exploiting that the expectation is a linear operator. So, it follows that E of y equal to expectation of Ax equal to A into E of x equal to A mu. Similarly, the variance of y can be found by using 51 the equation variance of y equal to variance of Ax, which is equal to A into variance of Ax into A transpose, which is equal to A into summation A transpose. This means the random variable y is distributed according to P of y equal to n of y over a mu into a summation a transpose of the random variable. Now we have a full rank matrix A in r power m cross n, where m is greater than or equal to n, and y in r power m is a Gaussian random variable. Then probability of y equal to n of y over ax summation. So this means corresponding probability distribution P of x, and A is invertible. We can write x equal to A inverse y, and then apply the transformation of the previous ideas. If A is not invertible, then approach is similar to the pseudo inverse, and we pre-multiply A inverse A transpose on both sides. Therefore, A transpose A, which is symmetric and positive for y equal to Ax, therefore A transpose A the whole inverse into A transpose y equal to x. Therefore, the linear transformation of y, and we obtain P of x equal to n of x by A transpose A the whole inverse into A transpose y, comma A transpose A the whole inverse into A transpose into summation of A into A transpose A the whole inverse. So, now we can incorporate it with the matrices and the diagonal of the matrix. So, in terms of the the conditional probability of these areas of n of this function. Now, we are going to discuss sampling from multivariate Gaussian distribution. For a general multivariate Gaussian, where the mean is a non-zero and covariance is not an identity, now we have a properties of linear transformation of a Gaussian random variable, and assume the generating sample xi, where I varies from 1 to n, is a multivariate Gaussian distribution with mean mu and covariance summation. So, we have a multivariate standard normal is n of 0 I. So, the multivariate normal is n of mu comma, that is mean comma covariance. We can use the property of linear transformation of the Gaussian variable. X belongs to n of mean is 0 and covariance is I. Then the linear combination y equal to Ax plus mu, where A transpose is a covariance summation, is a Gaussian distribution with the mean mu and covariance summation. So, by using the Cholesky decomposition of A, the covariance can be written as A transpose. So, the Cholesky decomposition has a benefit that A is a triangular and a leading coefficient of the computation. That is